Hi, this is Dan Steinberg at Salford Systems, and welcome to this particular edition of Salford Systems online training videos. In this session, we're going to be discussing the cart tree sequence. Cart follows a forward growing and backward pruning process to arrive at the optimal tree. In the process, cart generates for us not just one model, but a collection of progressively simpler models. This collection of models is known as the tree sequence. And this video segment will explain this forward-backwards tree generation process. We'll also discuss how a modeler might use judgment to select a near-optimal tree that might be better for deployment than the so-called optimal tree. Let's go back to our example dataset, the Euro Telco Mini Excel file. And again, let's set up our model, making sure to select a dependent variable, exclude the record ID, which we don't want in the model, and indicating that the city and the marital status are categorical variables. Now hit the Start button. We recall that the optimal model is revealed to have 40 terminal nodes, and in a previous video we discussed this particular tree, which has 10 terminal nodes. Now let's go into a little more detail as to what actually goes on during the cart tree growing process. The first thing to notice, we have a curve down below our tree topology graph, which is a downward sloping curve usually, till it hits a minimum, and then it starts to increase. This curve represents the performance of different sizes of trees on a test sample. In this case, the test sample was obtained by cross-validation, which we discuss in another video. For now, just take it on faith that we have an honest test-based methodology for determining how well the given trees perform. The lower this curve gets, the more accurate the model is, because this is a measure of error. And if we use our left and right arrow keys, we can move through a variety of different sized cart trees. So the question is, how do we get these trees? What does cart do? Well, move all the way to the left edge of this curve here to obtain the beginning of the cart tree, which always starts with the root node. In this case, the 830 records divided between 126 yes outcomes and 704 no outcomes. And then cart proceeds to split this root node, which is all of our training data, into two partitions. Cart always will split whatever node it is splitting into exactly two and no more nodes. Having split the root into two nodes, what cart then does is continue to split the nodes. However, the sequence that we see here is not the order in which the trees are grown. In fact, what happens, in order to get an idea of how the trees are grown, we need to go to the other end of this display, which is the largest possible tree. And over here, if we click on this enlarge button, whoops, we have to click up here, this enlarge button, now we get to see what the largest tree that cart developed was. The actual order in which cart grows the tree is known as left first. That is, cart starts at this root node here, then splits this left child here, then it splits the left child again, and then again to the left, and then again to the left, etc. In other words, cart favors making splits on the left side of the tree until it can't go any further, and then it gradually works its way across to the right. It actually doesn't matter how cart orders the splitting, because every node, no matter where it is analyzed in isolation from all the other nodes, and that node is searched for the best possible split that CART can find. So, order of tree growing and split making is irrelevant, and CART uses an ordering that is convenient for the programming of the software, and we end up with this largest tree. So this largest tree is our starting point. Now if we make it a little bit smaller, it's very hard to see the details here, but it gives you a rough idea of what the general topology and pattern of the tree is. You can see that it is quite deep on certain paths through the tree. It is relatively shallow on other parts of the tree. Why is that? Why does CART stop short on some paths and then not so short on others? Well, the answer is very simple. In some cases, CART simply runs out of data. What that means is if CART arrives at a node in which there's only one record, obviously the splitting has to stop. Also, because we're trying to separate zeros from ones or goods from bads, if we ever arrive at a node in which all the records are good, let's say, then it doesn't matter how many of them there are. If they're all of the same class, there is no further splitting that's possible. So those two reasons are going to be the principal reasons why a tree may have branches that are not as long in some directions and paths as in others. But the important point here is that we've gotten to a large tree. What is this large tree? This large tree is our raw material. This is the starting point from which we're going to try to discover a smaller tree which lives inside of this larger tree. And this smaller tree is going to have certain desirable characteristics. Among other features of this smaller tree is that it is going to be the best performer that we can find of all the trees that live inside this bigger tree. I'm going to click on this button over here again in order to make this curve visible throughout its entire range. So here we are at this biggest tree, which has 81 terminal nodes in it. And now our question is, how do I arrive at a smaller tree and also arrive at a tree which is perhaps more desirable than this larger tree, which is very likely too large, or, as it's known in the literature, overtrained? Well, the CART methodology introduces a special concept called cost complexity pruning, and the key idea here is that we want to remove from this tree something at the bottom, and we want to remove one of these splits, which is the split that hurts the performance of this curve the least on the training data. So this is something that's done automatically by CART, and CART checks every one of the bottom parts of the tree, the splits that lead to terminal nodes, and it calculates what the damage to the performance of the tree on test data would be if that particular split was removed. Finding the split that hurts the least, it pulls back to progressively smaller trees. So this methodology of cost complexity pruning is very helpful because it reduces the problem of finding a small tree inside of this largest tree to something quite manageable. The actual number of subtrees that exist inside of this relatively large maximal tree is some huge number, which is something akin to 80 factorial. It's smaller, but not that much smaller. So we have the equivalent of perhaps trillions of trees that we would have to estimate and analyze if we wanted to study every possible tree that is extractable from this larger tree. But given cost complexity pruning, the worst case scenario is that if our largest tree has 81 terminal nodes in it, then the largest number of trees that we have to assess in order to choose the best will be 81. That is, the slowest rate at which we can make our tree smaller is to eliminate one terminal node at a time. Sometimes we eliminate more, and we won't go into the details as to why, but essentially it has to do with ties that are available when we start removing nodes from the bottom of the tree. Why is cost complexity pruning so appealing? Well, here's one reason. Notice here I have a tree with 6 terminal nodes. What's special about this tree? Well, from cost complexity pruning methods, we can prove that this 6 terminal node tree is the best performer on the training data of any other possible 6-node tree. Now, what is another possible 6-node tree? Another possible 6-node tree could keep just the right-hand side of the tree and forget all about the left-hand side of the tree. And so we might get a tree that also has 6 terminal nodes, but looks quite different than this one over here, which is actually balanced and has both the left-hand side and the right-hand side. Why don't we produce a tree which consists of only splits on the right-hand side after the root node split? Well, the answer is that cost complexity pruning manages to eliminate that 6-node tree from consideration because it doesn't perform as well as the tree we have here. So this should help explain why the trees look like they do when you use your arrow keys to look through them. The shapes that we see do not reflect the order in which the trees were grown. They reflect the order in which the trees were pruned back. So we actually got to this sequence of trees by a backward process, but in order to start that backward process, we first had to grow that largest tree possible. Okay, so having this large collection of trees, what we can now do is test them on some independent data known as test data. And for each of these trees, what we can compute is the classification accuracy of those trees. This is what CART and the CART authors did in the original monograph describing CART. So if we go to the summary reports, click on prediction success, and then click on test, what we see here is the accuracy that we obtain for each of the two classes, the zeros and the ones. For the ones, our accuracy on test data is just shy of 70%, but for the zeros, it's at 51.7. Now that is for a specific tree, and it's a tree with 7 terminal nodes. If we were to go all the way out to the optimal tree, we go again to the summary reports, choose prediction success again, and go to test. And now we see that for the optimal tree, the performance is quite a bit higher. It is on test data, it's at 68%, about the same as we saw before. But for the zeros, our accuracy is now up to 73%. Now we can leave this up here and go back to a smaller tree. Let's go back to that 7-node tree again. And now we can compare these two. So you can see what happened as we got to the larger tree. As we got to the larger tree, which is 40 terminal nodes versus 7, our accuracy on the responders remains about the same, but our accuracy on the non-responders becomes much better. How do we accomplish that? By making finer distinctions in the data. And therefore, when we allocated certain segments to the response category, we didn't carry along a bunch of non-responders with them into that same segment. So let's close these windows now and go back to our navigator and observe some comments. First of all, if you're interested in area under the ROC curve, we're told here that the best that we can get on training data is with a 40-node tree. And we're also given the score on test data for the current size tree of 7 nodes. That's 0.60, which isn't so good. But if we go to the optimal size tree, now we get a score of almost 0.73, which is much better. So, do we have to take the optimal tree? And the answer is no. We have perfect freedom to decide to work with, to deploy, to score with, to report. We can deploy, score, or report any of the trees in this sequence. What would be our reason for choosing a tree which is different? Well, in most circumstances, people prefer smaller models to larger models. This number over here, the 0.585, is a number that goes between 1, which is the worst possible outcome, and 0, which is the best because it represents the degree of error. And we can use that particular score in order to compare different models. So we can see here that we've got an error score of 0.61 if we go to a model that has 35 nodes instead of 40. And as we get progressively smaller, we can see that that error score goes up, but we might be willing to make that trade-off, taking a little bit or a moderate amount of error in exchange for a smaller model. Now, when it comes to scoring, generally, it is not terribly relevant to consider the number of terminal nodes in the tree, unless we're talking about perhaps tens of thousands of nodes. But in smaller trees, it's not going to make that much difference whether we're working with 25, 30, or 40, let's say. But we may want to use a smaller tree not for scoring, but for interpretation and for decision making. And that's what we did in our first training video with this data. We decided to work with a 10-node tree, not because it is the most accurate tree, but because it tells an interesting story, and it's a story that can be used for segmentation and marketing purposes. How do we choose this particular tree? Well, one of the guidelines was simply whether we could present that tree on a single page. Doesn't sound like it's a particularly scientific basis for choosing a tree, but in real-world situations, if you have to defend a tree, you may decide to defend the tree which is slightly smaller than the tree that will be used when it's deployed onto servers, but which contains the essential predictive content of the main tree. And that's what we have over here. So when we go to this particular tree and look at the tree details, we see the story that we showed before and a story that is actually fairly compelling in explaining what this particular cart tree is doing. In general, you are always going to have a choice. And in general, there will be reasons for choosing a tree that is slightly different than the so-called optimal tree. One of the ways you can get a handle on the right size tree to explain or to comment on or to report is to click this button here. This button is a 3-state button. Let's continue to click it. This is its original status, which just shows this curve. When we click it once, part of this curve, consisting of blue little squares in a blue line, are turned green. And the green area is an area which we call the SE1 band, or the standard error 1 band. What does that mean? It means that the performances of all the trees that are colored green here are within 1 standard error of the measured performance of the optimal tree, which means that statistically speaking, it is not possible for us to be sure which of these trees would actually perform best on a new data set, that their performance is close enough that there is no compelling reason to choose one over another, and therefore we might as well choose the smallest tree in circumstances in which small is indeed beautiful. We can then go further than that by including judgment. So, to summarize what we've accomplished in this particular video, we've explained that CART starts with all the data in the root node and that it builds a large tree in an order different than we see in this tree sequence, and that large tree becomes the raw material for ultimately finding an optimal tree and other trees that are interesting. We then use the cost complexity backward pruning algorithm, which CART does for you automatically, which progressively makes the tree smaller and smaller and defines an interesting sequence of smaller and smaller trees. That sequence never goes slower than removing one terminal node from the maximal tree at a time. So if you have a 300 terminal node tree, the most alternative trees that you will see in the sequence will be 300. It then scores all those trees in that sequence using some form of test data if it has been available, and here we use cross-validation to do it. And this allows us to measure the performance of each of these trees and then to finally make a decision based on a combination of performance and judgment as to which tree we would prefer to work with. A final observation. Why is it that CART doesn't use a stopping rule and instead use this make a very large tree and then prune back to find the right tree? So why not use a stopping rule? Well, it turns out that the CART authors originally wanted to use a stopping rule, as this would allow trees to be finalized much more rapidly. But they discovered in their research that the problem with stopping rules is that they often stop too soon. In other words, they miss important structure that is available in the data, but discoverable only if you make a few more splits. The only way to protect against missing important structure in the data is to use the CART forward growing of a maximal tree followed by backward pruning. So why do some other tree growing tools use stopping rules? Well, here you're going to experience some of the advantages of working with TrueCART. CART makes use of some ingenious programming methods to accomplish massive amounts of computation rapidly. These high-speed algorithms are available only in the proprietary code written by CART co-author Jerome H. Friedman of Stanford University, and this CART is the only CART that was authored by Jerry Friedman, and it's the CART that is available only from Salford Systems. Competing trees often use stopping rules because their algorithms are slow, and they cannot complete the true CART process in reasonable time. These other trees often produce inferior results to TrueCart, even if they claim to be offering something like or a good facsimile of the CART algorithm. This concludes our session on tree sequences in CART. We thank you for joining us, and we hope to see you again in another one of our training videos. Until then, bye-bye.